Okay, today we're going to talk about inverse functions. I tend not to spend so much time talking about relations, which you remember don't have to have one y for every x. And we'll pretty much stick to functions. So there's only one y for any x value. And what happens is inverse functions are cool because all they really do is switch the x and y values. So let me give you an example. If you have a chart, x and y, and I'm going to make it horizontal. I don't often do that. And x is maybe 1, 2, 3, 4, and 5. And I don't know what the function is, but say I've got some y values of 7, 11, 25, 64, and 100. Okay. I can find an inverse function. So this y was equal to f of x, okay? I could find an inverse by switching the x and y values. So the inverse would be x's and y's, but what used to be y's are now x's. So 7, 11, 25, 64, and 100 are now my x's, but they have the same pairing. 7 is with 1, 11 is with 2, 25 is with 3, 64 is with 4, 100 is with 5. So all you really have to do is switch your x's and y's. Now we have a notation we like to use for inverse. If f of x is your function, then the inverse is denoted as f, and it looks like an exponent, -1 of x, but it's not an exponent. Let's be very clear. F is the name of a function whose input is x, whose independent variable is x. F to the -1 is called f inverse. You don't say f to the -1, you say f inverse is the way you read it. It looks like a superscript -1. Okay, not a subscript, but a superscript because it's above the line. So it's a naming thing. Okay, there's no -1 exponent, it's not taking a reciprocal, it's an inverse symbol. So that's our symbol. So we could have said this y was equal to f inverse of x. Okay? So we have our notation, and we know that we are reversing the x's and y values. So you can do that, reversing x and y's on a table like this, or any of our representations of functions, including a graph. So let's say we had a graph, and I'm going to pick a graph that maybe does, I don't know, let's see, something like this, okay, and maybe I'll label some points on here. So this is 0, 1, and maybe this is 2, 2, and maybe this is 4, 6. So that wouldn't be right, would it? Change 2, change 1, change 2, change 1. I gotta call that a 3. Okay, so that's my function. We'll label that one f of x. Then all I have to do is reverse the x's and y's, and I come up with the f inverse. So 0, 1 becomes 1, 0. Okay, and that would be right here. The 2, 2 becomes 2, 2. Well, that's interesting. That one didn't change. And this one becomes 3, 4, which would be, let's see, 1, 2, 3, 4 would be here. And that would be 3, 4, and I could draw that line. And so that's a graph of the inverse function, f inverse of x. So, find a couple of points on f of x, switch the x's and y's, draw those new points, and you have the inverse graph, okay? But what's really interesting about this being inverses is, and this will be true for all inverse graphs, that these are reflections across a line here that I've dotted. So imagine putting a mirror on this line, and you can see where the one graph is just a reflection of the other, okay, in a mirror across that line. So that's a reflection, and this line happens to be y equal x, okay? So it's making you switch from x to y and x and y to x. Okay, so they'll all do that. Let's try something else. Okay, before we go too much further, we want to ask ourselves, you know, does every function even have an inverse that we should be talking about? And the answer is no, not every function will have an inverse. Okay? So what happens is you want to have, yes, a function will have an inverse, yes, if it is a one-to-one function. So what do we mean by a one-to-one function? If you'll remember, a function has one y for every x. Okay? Or it passes the vertical line test. Is another way to do that. So you can look at this graph right here, and let's make a parabola. Does that pass the vertical line test? Yes. So therefore this parabola represents a function. So that's part of it, okay? But the second part of being one-to-one is for, let's put it this way, for every y, there's only one x. And then graphically we would do that with it's called a horizontal line test. Okay? So looking at this graph, you ask yourself, does this function, yes it's a function, but does it pass this horizontal line test? Crosses here, crosses there, and you have to say no, come on in. Okay, so we decided that this parabola fails the horizontal line test, therefore it is not one-to-one function, and if it's not a one-to-one function, it does not have an inverse. Okay, so in order to have an inverse, you must be a one-to-one function. And in order to be a one-to-one function, you have to pass both the vertical and the horizontal line test. Okay? Okay, so watch what happens. If we're going to think about inverse functions, what I'm going to do is I'm only going to draw half a parabola. So I'm going to draw the parabola, but only from one side. So I have this 0, 0 point. I have the 1, 1 point. Remember our special points? And I have the 2, 4 point. So what would be the inverse function of this? What would it look like? So I'm going to take these points and I'm going to reverse the x's and y's. 0, 0 stays 0, 0. 1, 1 stays 1, 1. But 2, 4 becomes 2. 2, 4 becomes 4, 2. So that's somewhere around here, 4, 2. Okay? And the way you connect the dots for this is you go up this time and over. Okay? And you can see what the inverse graph would look like. And again, like I said before, it is a reflection across this line. Okay? That goes down through y equal x. So that's cool. And what's interesting about this, if this is the graph, f of x is equal to x squared, as long as you follow the domain x is greater than or equal to 0, f inverse is equal to, this is actually a graph of the square root of x. Now I don't think we've graphed this before, but it is. And so it just brings up a point about another way to think about inverse functions, and inverse functions are undo each other. An inverse function undoes its function. Okay? So if you have a function and then you follow it with an inverse function, you basically undo what the first one had done. So it's kind of like taking the square root of x and then squaring it, you just get x. Okay? So square root x is inverse of x squared. Okay? Because a square root will undo a square. So the formal way to say that a function and its inverse will undo each other is this. If you took a composite, F inverse, composite F. Whoops, let me back up a little bit. F inverse composite F, okay? Then what happens is you are returned with X. So if you take this function and you start with your input X, the final output when you do both functions is right back where you started at the X, okay? And it's also true that F composite F inverse of X will also return you right back to where you started at X, okay? So when you take a composite of inverses, you didn't go anywhere, okay? You're just right back at X. So this is really a test for inverse. I can give you two functions and ask you, could you tell me if they are not inverse functions to one another? And you would say, oh, sure, let me take a composite and find out. So let's do an example of that. What if I told you, I'll give you two functions, f of x is equal to x plus 3, okay? And then I'm going to say, I think the other function, to undo adding 3, I think the inverse function would be subtract 3, okay? So there's that idea of undoing the plus 3, and I'm going to undo that with a minus 3. So let me take this composite and see if indeed I could write back at x. So if I took f, composite f inverse of x, remember how we start this, we always go back to the parentheses, f of g of x. I'm going to make that substitution. What is g of x? Oh, sorry, I should have put an f inverse here. Okay, that's an f inverse. So what am I going to put for that? I'm going to put the x minus 3 as my substitution. And now I go back to the f function, and I will replace x with the new input, x minus 3. So this x gets replaced with x minus 3, and then I have to do the plus 3, and lo and behold, that whole thing is equal to x. So I took a composite at equal to x. I'm good. It's great. Now, I do have to check both of them to make sure it works both ways. I'm going to save a little time. If I took f inverse composite f of x, I'll get f inverse of f of x, which is f inverse of x plus 3, which is x plus 3 minus 3, which is x. So there it is. I have proven that those two functions are inverse of one another. Okay? So let's go to the next one. I've shown you if I give you two functions, can you tell me if they're inverses? But now how do you find an inverse if you only have the one function? And here, this is a different question, but this is a nice one because we actually have a process to follow. So let me give you a function, f of x, and something a little more complicated, not much. I'm not quite sure how to undo that, okay? So I'm not going to make a guess like I did for x plus 3 and x minus 3. But I want to find this inverse. So here's the steps you're going to follow. Number 1, replace f of x with y. You know, we do that all the time. We use f of x and y interchangeably. So I have that first step. Second step, here's the really quirky thing here, is we're going to exchange x and y. So what was a y becomes an x, and what was an x becomes a y. Now, there is absolutely no mathematical basis, you know, that says that these two equations are the same thing. They're not. This is totally a made-up process. So don't ask me, how did I go from one step to another? It's this made-up process. Nothing in algebra says you can do that. But now I have this, I'm going to do my third step, and I'm going to solve for y. So take this and subtract 3 from both sides. And now I have to divide by 2. Y is equal to x minus 3 all divided by 2. And then I'm ready, I've solved for y, I'm ready for the fourth step, which is just a replace again. But this time y gets replaced with f inverse. I have found that inverse function. F inverse of x is equal to x minus 3 all over 2. And we are done and good to go. I want you to try this one on your own. Find the inverse by following that same four-step process to find the inverse of f of x is 1/2 x plus 3. I'm going to pause it and then show the answer when you're done. Alright, I got 2x minus 6 because the first thing I did was replace f of x with y. And then you exchange x's and y. So it was an x becomes a y, and what was a y becomes an x. Okay. Then I'm going to solve for y, so I need to move the 3 out of the way by subtracting on both sides, and then I'm going to multiply both sides by 2 to get rid of the 1/2 in front of y, so I have 2x minus 6, and finally I replace it with the symbol for f inverse, and I'm done.